Hello everyone, this is the solution video to 2024 AMC10 mock test. Let's do question 1. We have a water tank that is 30% empty, then 50 liters of water are removed. Now the tank is 30% full. How many liters does the full tank hold? So before the water is removed, we have 30% empty, but that's equivalent to 70% full. After the water is removed, is 30% full. Now we can see the change is 40%. That corresponds to 50 liters. So the capacity of the full tank will be 50 liters divided by 40%, which is 125 liters. So the answer is C. Question 2. Here we have n numbers. If one number is changed to 43, the average becomes 64. If this number is changed to 59, the average becomes 66. What's the average of the other n-1 numbers? Let's look at the change of the sum of the n numbers. On one hand, it's changed from 43 to 59, so the change is 59 minus 43. On the other hand, the change of the sum is the number of numbers n times the change of their average. Their average changes from 64 to 66, so it's changed by 2. We should have this equation. 59 minus 43 equals n times 66 minus 64. So this implies 16 equals 2n, which implies n equals 8. So there are 8 numbers. Now let's find the average of the other n-1 numbers. We can choose the first situation. When this number is changed to 43, the average is 64. So here we have 8 numbers, the average is 64, the sum is 64 times 8. So we subtract this number, 43, that will be the sum of the other n-1 numbers. Now we know n equals 8. So we divide by 8 minus 1, that is our average. 469 divided by 7, the answer should be 67. Question 3. Here we have 2 vehicles. One slow vehicle is moving ahead with speed 15 meters per second, length 25 meters. The fast vehicle is moving behind with speed 25 meters per second and the length 125 meters. Now the fast vehicle catch up the slow vehicle from behind. The question is, how long does it take to completely overtake? All right, let's see the moment when the fast vehicle start to catch up is the picture 1 I drew here. Now the moment when the fast vehicle completely overtake the slow vehicle is the following second picture. Let's think about the picture relative to the slow vehicle. So relative to the slow vehicle, the fast vehicle need to catch up such distance. If you look at the front of the fast vehicle, let me mark A. Mark A. The change of the distance is the sum of their lengths, 25 meters plus 125 meters. Totally, it is 150 meters. Now, let's think about the catching up speed. The fast vehicle has speed 25 meters per second. The slow vehicle has speed 15 meters per second. Relatively, the fast vehicle catch up by 25 meters per second minus 15 meters per second. So the speed of catching up is 10 meters per second. So we use the distance divided by the speed, that's the time. The distance to catch up is 150 meters divided by 10 meters per second, it is 15 seconds. So the answer is E, 15. Question 4. Here is a magical beanstalk, which produces a number of beans each day. Let B be the number of beans produced on a certain day. If B is less than 15, on the next day, it will produce 2B beans. If B is at least 15, on the next day, it will produce 2B minus 30 beans. So following this pattern, if today, on the first day, it produces 1 bean, how many beans will it produce on the 2024th day? So let's find the pattern of these numbers. On the first day, it produced 1 bean. Now 1 is less than 15. So that means on the second day, it will produce double of this number, which is 2. It's still less than 15. So on the third day, it will produce 2 times 2, 4 beans. On the fourth day, it will produce 2 times 4, 8 beans. On the fifth day, it will produce twice of 8 beans, which is 16 beans. Now 16 is larger than 15. Now, so on the 6 days, it will produce 2 times 16 minus 30, which is 2. And then on the 7th day, because 2 is less than 15, it doubles 2, so it's 4. 8th day doubles at 4, which is 8. 9th day, 16. So we see the pattern. The pattern is after the first day, the number repeats for every 4 days. 2, 4, 8, 16. 2, 4, 8, 16. That's the pattern. Now the question is how many beans will produce on the 2024th day? Now we should subtract the first day as 2023 days. For these 2023 days, it follows this pattern. So 2023 equals 4 times 505 plus 3. So there will be 505 such patterns, but we have additional 3 days. So that means it's the third number in this pattern. The third number in this pattern, which we can see is equal to 8. So on 2024th day, it will produce 8 beans. Let's do question 5. Here we have 2 equilateral triangles put together such that their opposite sides are parallel. So based on that, we can have every triangle here is an equilateral triangle. For example, we know angle here, let me call it X. Angle X is 60 degrees. But you know, AB is parallel to YZ, so angle XAB is also 60 degrees. Angle XBA is equal to angle Z is 60 degrees. So XAB, triangle XAB is an equilateral triangle. Similarly, any of other triangles is also equilateral triangle. Now we know their overlap is a hexagon. There are 4 sides. We know the lenses. We need to figure out the total perimeter. In other words, we need to figure out the lengths of EF and FA. So based on that, these triangles are equilateral triangle. We note that XB equals AB equals 6. Also, AX equals 6. Now, BC, we know is 15. Now, triangle CDZ is also an equilateral triangle. Since we know CD is 11, CZ is also 11. DZ is 11. Now we can see the side lengths XZ. XZ equals 6 plus 15 plus 11, which is 32. But since XYZ is equilateral triangle, so XZ should also equal to YZ. From here, you know, YZ equals YE plus 12 plus 11. From here, we can solve YE. Now, YE equals 9. Next, we know that EFY is an equilateral triangle. YE equals 9 implies EF equals 9. Also, YF equals 9. Then we go to the sine XY. Sine XY, on one hand, it's equal to 9 plus FA plus AX, which is 6. But we know XY is equivalent to XZ. XZ equals 32. From here, we can solve FA. 32 minus 9 minus 6, we got 17. So FA equals 17. So far, we solved the length for each side of the hexagon, and we can find the perimeter. The perimeter is 6 plus 15 plus 11 plus 12 plus 9 plus 17. It is equal to 70. The answer here is 70. Question 6. There are 5 candidates in the school election. After 3/4 of the votes are being counted, we have the following results. How many students still have a chance to win this election? Now let's count how many votes are already counted. That is 14 plus 11 plus 10 plus 8 plus 2, which is 45. 45 corresponds to 3/4 of total. Now we can solve the total votes. Total number of votes is going to be 45 times 4/3, which is 60. There are totally 60 votes. Now that means there are 15 more votes to be counted. Well, this 15 votes can go to any of these candidates. If all 15 votes go to Alex, so Alex will have 14 plus 15, which is 29. That's the highest number of votes. So Alex can win. If all these 15 votes go to Bella, so Bella will have at most 26 votes. That is the highest number of votes. So Bella can win. If all these 15 votes go to Calvin, he will have 25 votes, and obviously Calvin will win this election. And if all 15 votes go to Diane, she will have 23 votes. That's still the highest number of votes. So Diane has the possibility to win the election. If all 15 votes go to Eddie, Eddie will have 17 votes. That's still the highest number of votes. So we see that everyone has a chance to win this election. So the answer to this question is 5. Let's do question 7. Here, Emily has 12 beads, 3 red, 3 blue, 3 yellow, and 3 green. She will use these beads to make circular ring. Her brother take away some beads. The question is, what's the fewest number of beads her brother Billy could take away to make it impossible for Emily to create a ring where no 2 adjacent beads are of the same color? Now, make the question clear, let me introduce the following statement. Let's go to S. Statement S is, it's possible to make a ring where any 2 beads next to each other have different colors. So the question 7 says, what's the fewest number of beads Billy can take away so that S is no longer possible? S is no longer possible. So we can imagine that if Emily has more beads, it's more likely S is possible. So we can ask the question from the opposite direction. That is, what's the largest beads Emily can have, but as is not true. As is not true. She cannot make a ring with beads next to each other have different colors. So in order for this as to be not true, we should have more beads of the same color. Let's think about an extreme situation. We have 3 beads of the same color. For example, we have 3 red. In order for S to be not possible, we cannot have too many other beads, right? If there are 3 beads, we can separate this red beads. So in this sense, we can have at most 2 more beads. 3 red plus at most 2 more beads. So this will make S not true. So in this sense, for example, I have a blue, maybe 2 blues. We will always have 2 red beads next to each other. So S is not true. Now we can see that Emily can have at most 5 beads. So the answer to this question here is 5. Now we go to the answer to our question 7. That's the complement. So answer to this question is, because Emily has 12 beads in total, Billy need to take at least 7 beads. So Emily will have at most 5 beads, and that's possible for Emily to not make such rings. So the answer to question 7 is 7. Question 8. In the following equation, 2x plus ay equals 15. For how many positive integers a, the equation has at least one solution, while x, y are positive integers. Here we notice that 2 times x is always an even number. So a times y equals 15 minus 2x. If we have solution x, y, positive integers, we notice that 15 minus 2x must be an odd number. So ay is odd number. That just means a should be odd. And also y is odd. Next, we see that 15 minus 2x, if it's odd number, is at least 1, and at most 13, because x is at least 1. So we can only consider the cases that a is odd number between 1 and 13. A can be any odd number between 1 and 13. So there are 1, 3, 5, 7, 9, 11, 13. So for each choice of A, there will be corresponding value of y and x as the solution to the equation. So we see the answer to this question is 7. There are 7 cases. Let's do question 9. N is a positive integer such that n factorial equals 6 factorial times 7 factorial. What's the remainder when n is divided by 6? Now let's rewrite this product. It's 7 factorial times 6 factorial. Let me keep 7 factorial and write 6 factorial as 1 times 2 times 3 times 4, 5, 6. We are trying to solve n by writing this product as a factorial. Now we already have 7 factorial, so the next number should be 8. So let's find 8. It can be created from 2 and 4. So that gives you 8. Next, after 8, we need a 9. 9 can be created from 3 and 3. Here we have 1 3 from 6. So 6 is 3 times 2. So we can take 2 3 to create a 9. And finally, we have the number 5 and 2 left. They basically give us 10. So in this way, 7 factorial times 6 factorial equals 7 factorial times 8, 9, and 10, which is exactly 10 factorial. So in other words, we know that the number n is equal to 10. And 10 is 6 plus 4. So when it's divided by 6, the remainder should be 4. The answer here is E, 4. Question 10. What is the greatest common divisor of these two big numbers? So let's write the first number. A equals 2 to the power 2023 plus 2 to the power 2024. We can factor this common part 2 to the power 2023. So it's this number times 1 plus 2, right? Which is equivalent to 2 to the power 2023 times 3. Similarly, let's call the second number B is 3 to the power 2023 plus 3 to the power 2024. Now the second number can be viewed as 3 to the power 2023 times 1 more 3. So we can factor 3 to the power 2023 times 1 plus 3. In other words, the later part is 4. 4 is equivalent to 2 squared times 3, 2023. In this way, we can easily find their GCD. GCD of A, B is GCD of 2, 2023 times 3, which is just 3 to the first power, 2 squared times 3, 2023. So in order to find a GCD, we consider the greatest common factor for each prime factor. Both parts have 2, and both parts have at most 2 squared. That's the common part. So it's just 2 squared. That's the common part from prime factor 2. As for 3, the common factor is 3 to the first power. So in other words, GCD equals 4 times 3 is 12. The answer to this question is 12. Question 11. Rectangle ABCR is inscribed in the quarter circle SRT with radius 6. Now we know the perimeter of ABCR is 16. What's the approximate area of the shaded region if we take pi to be 3? So here notice that the perimeter of ABCR is twice of its length plus twice of its width. Let me just call the length AR to be X, the width RC to be Y. We have 2 times X plus 2 times Y is the perimeter, which implies X plus Y equals 8. Now, on the other hand, the diagonal of this rectangle is AC or BR. But we know BR is also the radius. So BR is equivalent to 6, the radius. And then we can use Pythagorean theorem such that we have x squared plus y squared is equal to, on one hand, it's AC squared. On the other hand, it's also BR squared, which is 6 squared. That is 36. So now we have the following equations. X plus y equals 8. X squared plus y squared equals 36. In order to solve the areas, we can solve x times y, which is the rectangle's area. So that can be derived from x plus y squared. On one hand, it's 8 squared, 64. That is x squared plus 2xy plus y squared. On the other hand, we know x squared plus y squared equals 36. So this is equal to 36 plus twice xy. From here, we can solve xy. So x times y is a squared 64 minus 36 and divided by 2, which is 14. Now, the shaded area is exactly the quarter circle's area minus 1/2 of the rectangle's area. The quarter circle's area is 1/4 times pi r squared. R equals 6. So 6 squared. And minus 1/2 of xy. So it's equal to 9 pi minus 1/2 of xy, which is 7. If you take pi to be 3, that implies 9 times 3 minus 7, the approximate area is 20. The answer to this question is 20. Question 12. In the game Prime Time, an interval of length 10 is randomly chosen between 11 and 39. Joey needs to find all prime numbers in this interval, but he has two misunderstandings. The question is, what's the probability that he still give the correct number? So here, let's think about how many different intervals are possible, because the probability is a quotient of two numbers, A over B. Here, B is the total number of cases. In this question, is the total number of possible intervals. Since here the interval is between 11 and 39 inclusive, we know that the interval with the smallest number is from 11 to 20. And the interval with the largest numbers is from 30 to 39. So in total, there are 20 intervals. In other words, we have the denominator b equals 20. We should find a, that is how many intervals based on Joey's misunderstanding, he still find the same number of prime numbers as the correct answer. So let's mark all prime numbers from 11 to 39. They are 11, 13, 17, 19, 23, 29, 31, and 37. Now, based on Joey's misunderstanding, he believes that all the multiples of 7 is prime. So between 11 and 39, there are two such numbers, that is 3 times 7, 21, 5 times 7, 35. So those two numbers are actually not prime, but Joey will think they are prime. So let me mark these two numbers with green color. I check 21 and 35 with green color. That means it will be included. Joey has a second misunderstanding. He thinks that for a true prime number whose digital sum is a prime, Joey falsely thinks it's not a prime. Let's check how many such prime numbers satisfy this requirement. We have 11 because 1 plus 1 is 2 is prime. So Joey will think 11 is not prime. Also 23, 2 plus 3 equals 5. Joey will think 23 is not a prime. And also 29, because 2 plus 9 is 11, which is prime. Joey will think 29 is not a prime. And there's no more. So based on this, how many intervals Joey will still give the correct number of prime numbers? So in other words, we need to find how many intervals, including 10 numbers, it includes a green check and one red cross. So we know it's impossible for 11 and 21 to be together because the length is over 10. So the first case will include 21 and 23. Include 21, 23, we should start from 14. Let me mark this interval. It should start at least from 14 up to 23. That's the length 10. And you keep increasing numbers from 15 to 24, from 16 to 25, so on, up to not touching next number, 29. So up to 28. So it should start from 19 to 28. Here we have totally 6 cases. Okay, the smallest interval is from 14 to 23. The largest one is from 19 to 28. We have 6 cases. For these 6 intervals, Joey will still answer the number correctly. Now, if we keep moving, we will include 29. That doesn't work. And keep moving, we will have the case that include 29 and 35. So to include 29 and 35, so it starts from 26. So from 26 to 35, for this interval, Joey will give the correct number. And we keep shifting the interval forward. Finally, in order to still keep 29, the largest intervals from 29 to 38. If we move forward, we don't have 29 anymore. So in this case, we have 4 such intervals. In total, we see that there are 10 such intervals. So for 10 such intervals, Joey will answer the number correctly based on his misunderstandings. So now that implies the numerator of the probability A equals 10. So probability is A over B. We know B equals 20. So it's 10 over 20. The answer is 1/2. Question 13. I think of 2 positive integers and call their sum S and their product P. Which of the following could not be the value of S plus P? Let these 2 numbers be X and Y. So X and Y are positive integers. Now we know that S is the sum, so it's X plus Y. P is the product, X times Y. So S plus P equals XY plus X plus Y. Now here we apply an important factorization formula. Think about if we add 1 to both sides. S plus P plus 1, xy plus x plus y plus 1, then we are able to factorize the right-hand side is equal to x plus 1 times y plus 1. And you know that x and y are at least 1. That just means x plus 1 is at least 2. Y plus 1 is also at least 2. Now let's check those choices. Which number will make this possible? If you look at A, we have 84 as S plus P. Now we need to add 1. 84 plus 1 is 85. It is possible to factorize into 2 numbers, each at least 2. For example, 5 times 17. We can take X to be 4, Y to be 16. Right? Similarly, let's do B, 86. If you add 1, we got 87. 87 can be factorized into 3 times 29. That's also good. And if you look at a C, we have 88. 88 plus 1 is 89. 89 is not factorable into 2 numbers. Both are at least 2 because 89 is prime. So the answer here is C. Let's also just check D and E to see they are possible. D 90 plus 1 becomes 91, can be factorized into 7 times 13. That's possible. E, we have 92. If we plus 1, it's 93, which can be factorized into 3 times 31. That's also possible. Say x equals 2 and y equals 30. So here the answer is C, 88. Question 14. Here we have 3 red balls and 2 black balls. Players A and B withdraw balls from the arm consecutively until a red ball is selected. What is the probability that A selects this red ball? So there are 2 cases. A can select a red ball in the first round. That is, in the very beginning, A got a red ball. And that's it. So since we have 3 red balls and 2 black balls, the probability of selecting a red ball is 3 over 3 plus 2, which is 3 over 5. But there's another case that in the first round, A does not select the red ball. And then B will not select red ball either. So in this case, we will have A, B both get black balls. But in the second round, A will for sure to select a red ball because there are 2 black balls only. The remaining balls are all red. So A will select a red ball. In this case, we have the probability as follows. In the beginning, A select a black ball. The probability is 2 over 5. Now after that, there's 1 black ball and 3 red balls. So for B, the probability of selecting black ball is 1 over 4. So this corresponds to 1 over 10. So if we add them together, that's the probability that A select red ball. 3 over 5 plus 1 over 10, which equals 7 over 10. It's already simplified. So 7 plus 10 equals 17, which is the answer here. Question 15. A lily pad is a disk with radius 1 that has a 60-degree sector cut out. Here we have 2 lily pads. Can fit in a L times 2 rectangle without overlap. Find the smallest possible value of L. So in order to minimize L, the length, we need to minimize the distance between their centers. So here's the case that happens, like the picture shows. We have each sector is tangent to some radius of the other sector. So let's call the tangent point to be A and B. If we connect O2 to A, now we know the sector is tangent at A. That means O2 is perpendicular to AO1. And here we know that angle AO1, O2 is 60 degrees. That means our triangle O1, O2A is a special triangle. That is, the angles are 30 degree, 60 degree, 90-degree triangle. Such a triangle, we can find the ratio of their sides. The AO1 to AO2 to the hypotenuse O1, O2 must be 1 to root 3 to 2. Now let's use this information to solve the distance from O1 to O2. We notice that AO2 is the radius, which is 1. That implies AO1 is 1 over root 3. And then we have O1, O2 is twice of AO1, which is 2 over root 3. Now we can find the total distance. The length L It's basically 1 plus the distance between O1, O2, and plus another one. So totally we have 2 plus 2 over root 3. That's the length of L. So the answer here is C. Question 16. How many positive integers from 1 to 2024 can be written as the difference of the cubes of two consecutive positive odd numbers? So let's think about how to express odd numbers. We know that the kth odd number is equal to 2k minus 1. For example, the first one is 1, the second one is 3. So that's why the first number is 26, because that's the second odd number cube minus the first odd number cube. And next one is 98 because it's the third odd number cube minus the second odd number cube. The question is how many? How many such numbers are up to 2024? Let's see. Suppose we have k such numbers. You know this difference is increasing. Consider the difference between k plus 1's odd number. So that is this number. This is the k plus 1's odd number minus the k's odd number, 2k minus 1. That's the largest case. So we have that to be less equal to 2024. Then let's try to solve k. What's the largest k? Right. So here we can simplify it. 2024 is bigger equal to, here's 2k plus 1 cube minus 2k minus 1 cube. If we expand it, we can simplify into 8k cubed plus 3 times 2k squared times 1 plus 3 times 2k times 1 squared and plus 1 minus 8k cubed minus 3 2k squared times 1 plus 3 2k times 1 and minus 1. That's the difference. After simplification, this is equal to 24k squared plus 2. Now we can just solve k squared to be less equal to 2024 minus 2 divided by 24. So that's about 84. So we can conclude k squared is less equal to 84. But now k is an integer, so that means k is at most 9. At most 9. So the answer is 9 to this question. Question 17. Two wheels are fixed to an axle as shown. They have different sizes. When this is put on the ground, it traces out 2 circles with the same center. What's the radius of the larger circle? So let's draw the ground horizontally and the wheels put on the ground. We can extend the axle so it touches some point that's called O. This O is supposed to be the center of the larger circle. And let me call this point to be A. So OA is the radius we're looking for. All right, we use this given data. For the larger wheel, the radius is 105 centimeters. The smaller wheel has radius 70. And here's 90 degree, 90 degree. The axle has length 120 centimeters. So we call this B, C, D. So we can draw a line passing through B that is perpendicular to these wheels. Let me call it E. Now we can find AE is the difference of their these two radii. So AE is AC minus EC. AC is 105 centimeters. EC is just a BD, right? EC is equal to BD, which is 70. So AE equals 35. Let me put 35 here, AE. And we know EB is just 120. EB equals CD equals 120. So by Pythagorean theorem, we can solve AB. Right? Actually, we note that AE, BE are both multiples of 5. So let me write here. AE is 5 times 7, and the BE is 5 times 24. So this right triangle is 7, 24, 25 triangle. So we can solve AB is 5 times 25, basically. So, or you can just use the formula. 7 squared plus 24 squared square root and times 5. So it's 5 times 25, it's 125. So AB equals 125. In this way, we know that triangle ABE is similar to triangle AOC. We're trying to use similarity to find length of AO. Now we can find their ratio. So AB over AO is equivalent to AE over AC, which is 35 over 105. Now we already know AB equals 125, so we can solve AO. See, AO is AB times 105 over 35, which is 125 times 3, which is 375. So that means the radius of the larger circle is 375 centimeters. So we need the digital sum. The digital sum is 3 plus 7 plus 5 equals 15. So the answer to this question is 15. Question 18. Here we have floor function, which takes the integer part of any number. And the function here is defined based on the floor function. Let's call it f of x. Is the integer part of x over 20 plus the integer part of x over 24. X is any positive integer between 1 and 2024. The question is how many different integer values this function can take. First, we notice that the minimum value is 0. When x equals, say, 1 or 2 or some small number less than 20. And when x increases, f will not decrease. Sometimes it will increase, sometimes it does not change. As x increases, fx may not change or may increase, right? When does this change happen? There are two cases. Fx increases in the following cases. Case 1, when x is a multiple of 20. So it will increase to the next integer. It's an integer. For example, if x is 19, x over 20, the integer part is 0. But when x increases from 19 to 20, the integer part becomes 1. It increased by 1. Similarly, we have case 2, where x over 24 is an integer. Now let's count how many such numbers are possible. First, for the case that x is a multiple of 20 up to x equal to 2024, we can see there are 2024 divided by 20. If we take the integer part, the largest value is 101. So there are 101 cases. At this 101 numbers, the first part increased by 1. Now, second part, they are 2024 divided by 24. The largest multiple equals 84. For the first floor function, it increases 101 times. For the second floor function, it increases 84 times. Now we can find the maximum value. The maximum value equals 101 plus 84, which is 185, right? So the function value is between 0, the minimum value, and 185, the maximum value. However, there are some numbers not achieved by function f because there are cases that both parts increase by 1. For some x, both x over 20 and x over 24 are integers. Let's count how many such cases. If x is a multiple of 20 and 24, it must be a multiple of their LCM, least common multiple. Least common multiple of 20 and 24 equals 100. So then there are 2024 divided by 100. If we take the integer part, it's 16. There are 16 cases that the function increases by 2. Both parts increase by 1, so it totally increased by 2. In other words, between numbers from 0 to 185, there are 16 numbers not achieved because it increased by 2. So now the answer to this question is between 0 to 185, there are 186 cases, but there are 16 numbers not achieved. So the answer is 170. So the answer here is B, 170. Let's do question 19. Here, A, B, C, D, A prime, B prime, C prime, D prime is a right prism with all edge lengths equal to 2 and BAD equals 60 degrees. So if that's the case, we have B prime, A prime, D prime is also 60 degrees. We have BCD is also 60 degrees. And B prime, C prime, D prime, 60 degrees. In other words, if we connect, say, BD, you can see the top face is essentially 2 equilateral triangles with side lengths 2. ABD, CBD are both equilateral triangles. I can also do that for B prime, D prime. Right, so that's the basic setting. Triangle ABD, triangle BCD, triangle A prime, B prime, D prime, triangle B prime, C prime, D prime are equilateral triangles with side equals 2. Now we're going to draw a sphere. The sphere is centered at D prime with radius √5. The question is, what's the length of the curve formed by the intersection of the sphere and the side face BC, C prime, B prime? So let's first find this curve. The curve is the intersection of the sphere and the side face BC, C prime, B prime. That means this is all points on BC, C prime, B prime that have distance root phi to point B prime. Let's find all such points. First, we can find the intersection with these two edges, like C, C prime, B, B prime. You know that we have D prime, C prime is perpendicular to C, C prime. So here's right angle here. And D prime, C prime is 2. So the intersection must be on the midpoint of C, C prime. Let's call it M here. So M is the midpoint. That means C prime M is 1. So we have, okay, C prime M equals CM equals 1. So we will have D prime M equals, by Pythagorean theorem, right? 2 square plus 1 square and take square root, that's root phi. So the intersection of the sphere on CC prime is M. Similarly, the intersection of the sphere to BB prime is also the midpoint. So B prime N is 1 here. So if I draw the radius, that's the radius. We also need to find other points on these faces with distance root phi to D prime. So here we can draw height from D prime to B prime C prime. Let me draw it here. Since we know this is an equilateral triangle, B prime, C prime, D prime is equilateral triangle, let me call this foot to be H. We draw D prime H perpendicular to B prime C prime. That implies C prime H equals B prime H equals 1. Equals 1. Now the distance from the curve, let me draw the curve here. All right. Let me draw the curve here. The distance from any point on the curve to D prime is equivalent to the hypotenuse of triangle D prime HP. That's because we have D prime H is perpendicular to the face B, C, C prime, B prime. So that means we always have D prime H P is 90 degree. So that means triangle D prime H P is a right triangle. And we know the radius D prime P is root 5. D prime P is root 5. And we know D prime H is root 3 as the height of the equilateral triangle with side length 2, right? Because C prime H is 1, C prime D prime is 2, so D prime H must be equal to root 3 here. Now we can find the distance from H to P. HP is D prime P squared minus D prime H squared. It's equal to root 2. 5 minus 3, 2, the root 2. So in other words, this curve is the arc of some circle with radius root 2 and with center H. The curve is an arc with center H and the radius equals root 2. So let's figure out this length. So here is this arc. Let me draw this arc here. Here we have M, here we have N, the center is H, the distance is root 2. Now, what we need to figure out is the central angle. Notice that MN, because MN are both midpoints of these two vertical edges. So MN is equal to the side length, BC, which is 2. So MN equals 2. And we know HN equals this radius root 2. That implies the angle NHM equals 90 degree. And HM is 90 degree. That means that this arc is a quarter arc of a circle with radius root 2. So the length is 1/4 of that circle, 2 pi radius root 2. So it's root 2 over 2 pi. That is the length of this arc, which is the answer to this question. Question 20. Consider the line defined by the following equation and the circle given by the following equation. These two curves intersect at points A and B. What's the smallest possible length of the line segment AB? So let's rewrite this equation of the line. We put A together. That's A times x minus 1. And B, we have B times y plus 2 equals 0. So this line passes through some fixed point, which is 1 minus 2. So this is a line passes through the point 1, negative 2. Now let's look at the circle. The circle, we can rewrite it into x squared plus y squared plus 4y equals 1. Now, in order to complete the square for y, let's add 4 on both sides. In this way, the left-hand side is x squared plus y plus 2 squared equals 5, which is just root 5 squared. That is a circle with radius root 5 with center 0, minus 2. So let's sketch this curve. A circle with the center 0, minus 2, x-axis. Here's the y-axis. Right, that's called a origin O. The center, that's called a P, which is minus 2 in a y-coordinate. And the line passes through the fixed point 1 minus 2. Here's 1 minus 2. Let's call it Q. Q is 1 minus 2. Now we're looking for the general situation. For example, we have a line maybe this way. They have intersection AB. What's the smallest length of AB? We claim that AB is minimized when the line is vertical. Claim AB is minimized when AB is vertical. This is related to the distance formula for the chord. So in general, let me draw a circle with center P, and we have a chord AB. Now, how to find the length of AB? We draw a line PH perpendicular to AB. Now we have right triangle PAH. So by Pythagorean theorem, we know AB is equals twice of AH because PAB is isosceles triangle. But AH by Pythagorean theorem is PA squared minus PH squared. We take square root. So PA corresponds to the radius. PH is the distance from P to the line AB. So that is R squared. We have twice here. R squared minus D squared times 2. So in order to minimize AB is equivalent to maximize D. If D is largest, AB is smallest. Now, in our situation, if AB is not vertical, the distance will be smaller than PQ. So D is always less equal to PQ. D is equal to PQ when AB is vertical. So in this sense, we can find the minimum length. Minimum length of AB is equal to twice of the radius PA. Radius here is root 5 minus D, okay, which is PQ. That's 2 square root 5 minus, okay, PQ equals 1. So it's equal to 4. So the answer to this question is 4. Question 21. Here we have trapezoid ABCD. AD is parallel to BC. Angle DCB is 45 degrees. Now E is a point on CD such that BAE is a isosceles right triangle. AB equals AE. In other words, angle BAE is 90 degrees. And angle ABE is 45 degrees. Angle AEB is also 45 degrees. Now we have AD equals 2 and DE equals 1. The question is to solve BC. So here, a key helping line is we draw a line from E that is perpendicular to DC. Let me call it EF. So in this way, we know that angle C is 45 degrees. Angle CEF is 90 degrees, which implies angle EFC is 45 degrees. So if that's the case, we have the angle BFE is 135 degrees. Also, because we have AD is parallel to BC, and the angle C is 45 degrees, this implies angle D is 135 degrees. So it's 180 minus 45, 135 degrees. Now, if we check some other angles, we can show there is a pair of similar triangles. Let's look at triangle ADE. In triangle ADE, since angle D is 135 degrees, so we have angle DAE plus angle DEA is 45 degrees. Because we have drawn this perpendicular line EF perpendicular to DC, and the angle AEB is 45 degrees. That implies angle BEF plus angle DEA is 90 degrees minus 45 degrees, so 45 degrees. From these two equations, we have the conclusion that angle DAE equals angle BEF. Let me mark it. Angle DAE here is equals angle BEF. So we have angle D is 135, angle BFE is 135. So we have similar triangles. Triangle ADE is similar to triangle EFB. Since they're similar, we can have the sides, corresponding sides are proportional. So here we have BF over ED equals EF over AD equals BE over EA. But we know that BE is the leg of isosceles right triangle. EA is the leg of isosceles right triangle. BE is the hypotenuse. So that means we have this ratio. BE over AE is equal to √2. So if we apply that ratio to these two quotients, we can have the following conclusion. For example, BF equals √2 times ED. ED equals 1, so BF equals √2. Second, EF equals √2 times AD. Since AD equals 2, so EF equals 2. 2√2. EF equals 2√2. Now we have that triangle EFC is isosceles right triangle. So that implies FC equals √2 of EF. Now EF is 2√2, so FC becomes 4. This gives us the length of BC. BC equals BF plus FC. BF equals √2. FC equals 4. So the answer is 4 plus √2, which is C. Question 22. In a tennis single match, it was planned for each pair of two players to compete in one match. Here we have 4 players. Let's call these 4 players A, B, C, D. In reality, these 4 players only played 2 matches, each of them. So as a result, a total of 41 matches were played. The question is, how many matches were played among these 4 players? Let's call this number X. So we're going to solve X. First, we denote by N the number of total players. Now, as planned, each pair of 2 players should compete in one match. So, as planned, they are, and choose 2 matches. And each player should play N-1 times. Now, for these 4 players A, B, C, D, each of them only played 2 matches. So we can compute how many times they did not play. Number of times A, B, C, D did not play. Each person is supposed to play N-1 times, but they actually only play twice. So each person didn't play N-1 minus 2 times. And there are 4 players. Let's multiply by 4. This is the total number of times they did not play. And among A, B, C, D, they played X matches. So if as planned, they are supposed to be 4 choose 2 equals 6 matches. Now they played X matches. That implies 4 choose 2 minus X, which is 6 minus X matches not played. So that corresponds to twice of 6 minus 2 minus X times not played. We know the total number of times not played is n minus 1 minus 2 times 4. Here we got sum happened among A, B, C, D. That's 2 times 6 minus X. The other parts are the times not played between A, B, C, D and the other n minus 4 players. So within A, B, C, D, we have 2 times 6 minus X times not played. Between A, B, C, D and the other n minus 4 players, how many times they did not play? That is n minus 1 minus 2 times 4 minus those not played within A, B, C, D. Okay, we can compute how many matches they did not play in total. So within A, B, C, D, we already know 6 minus X matches not played. Between A, B, C, D and the other n minus 4 players, we have each time corresponds to 1 match. So here is just n minus 3 times 4 minus 2 times 6 minus X matches not played. Now we know there are only 41 matches played, so we have the following equation. Total number of matches supposed to be played, n choose 2, minus those matches not played, 6 minus X, minus n minus 3 times 4, minus 2 times 6 minus X, equals 41. So we got an equation concerning n and x. So after simplification, we have the following equation. It's quadratic equation in n squared minus 9n minus 46 plus 2x. We are supposed to solve x. We know that x is between 1 and between 0 and 6. So x is larger equal to 0, less equal to 4, choose 2 equals 6. So we can check for what kind of x the above equation will have integer solution n. For example, if x equals 0, we have equation m squared minus 9n minus 46 equals 0. No integer solution for n. If x equals 1, we have n squared minus 9n minus 48 equals 0. No integer solution. Still no integer solution. Now let's check x equals 3, x equals 2, n squared minus 9n minus 50 equals 0. No integer solution. Next, x equals 3. So we have n squared minus 9n minus 52 equals 0. This time we have integer solution because we can factorize that into n plus 4 times n minus 13 equals 0. We have n equals 13, which works. Let's also check other cases. If x equals 4, we have n squared minus 9n minus 54 equals 0. No integer solution. If x equals 5, n squared minus 9n minus 56 equals 0. No integer solution for n. So x equals 6, n squared minus 9n minus 58 equals 0. No integer solution. So by checking all cases, we know that there's only one case works. That is when x equals 3. So we conclude that x equals 3. 3 is the answer to this question. Question 23. For how many prime numbers p, the following cubic polynomial has 3 positive integer solutions. Here a is a positive integer. So here let's review the other formula for cubic polynomial. Suppose we have a cubic equation x cubed plus lx squared plus mx plus n equals 0. If it has 3 roots, let's call it x1, x2, x3, then we must have the sum of the roots, x1 plus x2 plus x3 equals minus L. The sum of the product at each pair of 2 roots, x1, x2 plus x2, x3 plus x3, x1 equals n. And the product of 3 roots, x1, x2, x3 equals minus n. This is the Vieta formula for cubic polynomial. Now let's come to our question. In our problem here, suppose we still have 3 roots, 3 positive integer solutions. Let's call them just x1, x2, 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 x3 still. Now by Vieta formula, we know that the sum of the roots is x1 plus x2 plus x3 equals 3p minus 4. And the product, which is x1 times x2 times x3, is equal to 24p. Of course, a is computed by x1, x2 plus x2, x3 plus x3, x1. But here, let's focus on the sum and the product. Now we know the product is 24p, p is prime. We can discuss what are those roots. So p is a prime number. It cannot be split in further, right? So we can split 24p in the following couple ways. Maybe one root is p. The other roots multiplied to 24. It could be 1, 24. It could be p 2, 12. It could be p 3, 8. It could be p 4, 6. We can switch order. So basically, those are the cases that if p is one solution. Let's discuss each case. In this case, we know the sum will be p plus 1 plus 24, so it's p plus 25. It's supposed to be equal to 3p minus 4. That helps us to figure out p. Here, p equals 29 over 2. This is not a prime number, so this case does not work. Second case, the sum is p plus 2 plus 12, so it's p plus 14. It should be equal to 3p minus 4. That implies p equals 9. But 9 is not a prime number, so this case will not work. The third case, the sum is p plus 3 plus 8, which is p plus 11. It's equal to 3p minus 4. Here we can solve p equals 15 over 2. It's still not a prime number. It's not an integer. Now let's discuss p for 6. In this case, we have the sum equals p plus 4 plus 6, so it's p plus 10. It should be equal to 3p minus 4. This implies p equals 7. Okay, this case works because 7 is a prime number. Accordingly, we can solve a, right? We can solve a. A is 4 times 6 plus 6 times 7 plus 7 times 4. So we can solve a is 94. So this case works. Well, we may also have a case that one root is a multiple p, not just one p. It could be 2p. Suppose one root is 2p. So the other root should multiply to 12. So it could be 2p, 1, 12, 2p, 2, 6, 2p, 3, 4. Right? If we can switch order, that covers all cases. Now, if it's 2p, 1, 12, we know the sum is 2p plus 1 plus 12. So it's 2p plus 13 is equal to 3p minus 4. Then we can solve p equals 17, which is a prime number. So this case also works. Accordingly, you can solve a. We can solve a. We can solve a is the root is 1, 12, and 34. So 1 times 12, 12 times 34 plus 34 times 1. That's the value of a, which is 454. Now let's keep discussing the following cases. If the three roots are 2p, 2, 6, we have the sum to be 2p plus 8 equals 3p minus 4. So we have this case p equals 12, which is not prime, so this doesn't work. Finally, 2p, 3, and 4. The sum equals 2p plus 7. It is equal to 3p minus 4, so we get p equals 11. This case also works. And accordingly, you can solve a. A is 3 times 4 plus 4 times 22 plus 22 times 3. So it's equal to 166. Now, we discuss the case that we have root p and 2p. And we note that the sum of three roots is 3p minus 4, which is less than 3p. So that implies we cannot have like 3p as a root, or maybe 4p as a root. So that just means there's no more case. No more cases. We only need to discuss p and 2p. So here we have three cases. P equals 7, a equals 94, p equals 17, a equals 454, and p equals 11, a equals 166. So the answer to this question is 3. Here are 3 such p's. Let's do question 24. Two students, A and B, participate in a sport event. There are totally 6 events. Let's call this event 1, 2, 3, 4, 5, 6. Now, if they only choose one common event, that's the fact, okay? They only choose one common event. What's the probability that A registered for more events than B? So here we'll notice that the probability of the number of event A registered is bigger than the number of event B registered. That number is equivalent to the opposite case. The number of A is less than number of B. We have this symmetry. Of course, there's another situation that is the number of A equals the number of B. So in total, we have P, probability A, number of A larger than number of B, plus probability of number of A less than the number of B, plus number of A equals number of B, the probability. So that's all cases. So sum of these probabilities should be 1. Now our answer is probability of number of A is bigger than the probability of number of B. It can be computed through 1 minus the probability of number of A equals the number of B over 2. So finally, let's go to find the probability of number of A equals number of B. So here we have the fact that they only choose one common event. So let me use a graph to denote. This is event A registered. This is event B registered. And this box means total cases of events, all events. Okay, now they have one common event. That's in the very center, the intersection of AB. This common event, there are 6 choices, so it's 6 choose 1. There are 6 cases to determine this common event. Next, let's consider the cases for the other 5 events. For the other 5 events, let's see each of the other 5 events. There are 3 cases. Maybe this event is chosen by A. Chosen by A only. Chosen by B only. And not being chosen by A or B. Not registered. So there are 3 cases. So now we can think about a total number of situations. Total number of cases to arrange those events, to discuss which event A registered, which event B registered, based on the fact that A and B have only one common event. This is equal to 6 choose 1 times 3 to the 5th. Because for the other 5 events, each event, there are 3 cases. 3 times 3 times 3 times 3 times 3. So the total number of cases is 6 choose 1 times 3/5. That's supposed to be the denominator of the fraction in the probability. Now let's consider the cases that the number of A equals the number of B. Cases that number of A equals the number of B. Now, case 1, because they have one common event, so number of A equals number of B could be just equal to 1. In this case, all other 5 events are not registered by A or by B. So one case. 2, number of A equals number of B equals 2. So we discussed the other 5 events, right? So for the other 5 events, we have 5 choose 1 for the other event A registered. Now B should choose a different event from the remaining 4 events. So B will have 4 choose 1 ways to select B's second event. Okay, third case, number of A equals number of B equals 3. Now they already have one common event, so each of them should register two more events from the remaining five events. For A has five choose two ways to register two more events. After that, there are three events left. Now B should choose two from these three events. Three choose two. That's the number of ways. And we claim that it's impossible for A and B to register more than three events, but only have one common event. For number A equals number B larger than 3, and they have only one common event. Because there are only 6 events in total. If they have one common event, there are only 5 events left. It's impossible for each of them to register at least 3 more events, but there's no overlap, right? That's not possible. So in this case, we can consider the total number of cases, number A equals number B. Well, in the beginning, of course, each of them should choose this common event, 6 choose 1, right? So number of A equals number of B. This case is 6 choose 1 times 1 plus 5 choose 1 times 4 choose 1 plus 5 choose 2 times 3 choose 2. So after simplification, that's 6 times 51. Now we got this number is the numerator of the fraction for the probability. So probability of number of A equals number of B is the above number 6 times 51 over the original total number 6 times 3 to the 5th. Okay, that's the number. After simplification is 17 over 981. Our answer to this question is here. Our answer is 1 minus 17 over 81 and divided by 2. So this number is equal to 32 over 81. That is the probability in this question. The answer is A. Question 25. In this problem, there are 3 different vegetables to be planted in 3 different vegetable beds for 8 years based on some requirements. For simplicity, let's denote tomatoes to be 1, beans to be 2, and carrots to be 3. So every year there should be 1 for tomatoes, 1 for beans, 1 for carrots. So every year there should be 1, 2, 3. We have 3 vegetable beds near kitchen, near laundry, and near shed. To schedule this planning, it's equivalent to put these numbers into the following grids. They are totally 8 years. And draw 8 columns for the schedule. Now let's look at the rules. First, every year there should be 1 for tomatoes, 1 for beans, 1 for carrots. That means each column is a permutation of 1, 2, 3 in some order. Second, it says that a bed that has tomato in one summer can't have tomato in the next summer. That means after 1, on each row, after 1, it can no longer be 1. Moreover, we cannot have tomato for the year after next year. So if this year is 1, next year maybe 2 or 3, but the year after next year, it still cannot be 1. That's the requirement for 1 for the tomatoes. We also have some requirement for beans and the carrots. That's 2 and 3. So after beans, it cannot be carrots. So after 2, it cannot be 3. This cannot happen. So those are all the requirements to put 1, 2, 3. Now let's look at the schedule. We notice that the tomato, the ones, they only have influence to itself. So let's try to schedule 1 first. Step 1, schedule all the ones. Notice that 1 will have influence for the future 2 years, or in certain year, the schedule for 1 only depends on the previous 2 years. So we can consider the first 2 years how to schedule ones. You know that in the first year, it's totally free. For first 2 years. For the first year, it's totally free. It can be planted in any bed. There are 3 ways. And the second year, since the year that had tomato last year cannot have tomato, so there are only 2 ways. So in total, there are 6 ways for planting tomatoes in the first 2 years. To plant tomatoes for the first 2 years. Let me just quickly show these 6 cases. In the first case, 1 can be here, and the next year 1 may be here, or 1 may be here. If the first year 1 is in the middle, the second year 1 can be on the top or on the bottom. The first year 1 can be on the bottom, the second year could be on the top or in the middle. So there are 6 ways. Next, we claim that each such plan will determine future schedule uniquely. Step 2. For each of the above schedule, it determines all future schedules for ones. So let me just take one example. For the other cases, we have similar discussion. Let me just take this example. So if the first year is on the top, the second year is in the middle, we claim that the future years are just fully determined. For a year, for whatever years, that's totally determined. Suppose we have 1 year already fixed, 1 year already fixed. Now, if you go to the third year, it has to be the third row. It has to be the third row. And if you go to the fourth year, it has to be the top row, because after 1 cannot be 1, and after 1, for 2 years, it still cannot be 1. So for the 5th year, it must be in the middle. The 6th year, it has to be on the bottom, and next one is on the top, and then in the middle. So we can easily see this clear pattern. This kind of idea applies to other 5 cases. So here, let me just discuss the first case. The claim is that if you determine the schedule for the first 2 years, it will determine all future schedule for 1. Now that's good. So let's consider the next part, how many ways we can put 2 or 3s. That is step 3. Based on the above, let me just take this schedule. Based on the above schedule for 1, let's find the number of schedules for 2 and 3. For 2 and 3. So here we apply the idea of recurrence relation. Idea is recurrence relation. We're going to generalize this problem for n years. Let an be the number of schedules for 2 and 3 in n years. And in this problem, here we need A8. Here we need A8. If we can solve A8, our answer to this question should be 6 times A8. So the answer to this problem is 6 times A8, because there are 6 ways to plan 1s. And based on each one, we have A8 ways to do 2 and 3. All right, let's find A8. We will use AN first. Now for recurrence relation, we first consider for small n's. For n to be 1. For n to be 1, that is just 1 year. Based on the above schedule, we have 1 on the top. So 2 and 3 will have 2 ways to schedule. Either 1, 2, 3 or 1, 3, 2. 1, 2, 3 or 1, 3, 2. That just implies A1 equals 2. Next, let's consider A2. That is, for 2 years, how many ways we can schedule 2 and 3? There are actually 3 ways. Let me show these 3 cases. All right, well, first, let me put a 1, 1, that's fixed. Now, we discussed 2 and 3 for the first year. For the first year, it's totally free. It can be 1, 2, 3 or 1, 3, 2. If it's 1, 2, 3, the next year could be 2, 1, 3 or 3, 1, 2. Could be 2, 1, 3 or 3, 1, 2. There's no contradiction. Everything is satisfied. Now, the other case is the first year is 1, 3, 2. But the requirement is that after 2, it cannot be 3. So the third column cannot be 3. 3 has to be on the third row, cannot be 3. 3 has to be on the first row. That means the third row has to be 2. This is only one case. So totally, we have 3 cases. That means A2 equals 3. Right, that's like the beginning 2 cases. Now for recurrence relation, we're going to derive a relation between AN and A for small n's. For example, AN minus 1, AN minus 2. Here, let me first put a claim. We claim that for n larger equals to 3, we have AN is equal to AN minus 1 plus AN minus 2. If we have that, we can solve AN starting from A1, A2. Now, let me show you why this is true. Now, for the n-year case, we have this long schedule. Let's look at the last year or last few years. This is year N. We know there's one box with one. It depends on N. One can be on the top, can be on the middle, can be on the bottom. But for each case, the discussion is similar. So here, let me assume one is just on the top. If one's on the second row, the later discussion will be similar, and we have the same conclusion. So let me just discuss the case one's on the top. Now, based on our pattern, for one, in such case, if on certain year one is on the top, the previous year one is on the bottom, the year before that the one's in the middle. So we can determine the one from previous years here, and before that it's one here. Now we're going to discuss the schedules for 2 and 3 backwards. Now in the year in the nth year, we should put 2 and 3. There are basically two cases. Maybe it's 1, 2, 3, or 1, 3, 2. One, three, two. Of course, we have one here, one here, one here, one here. Now, let's see how it goes for this case. The last year is 1, 2, 3. We notice that before the last year, it's just any case with n-1 years. So here we have early years schedule. We notice that this part will never have any violation of the rules, because here one is before 3, right? We will not have 1 after 1 anymore. We will not have 2 before 3 anymore. So this is any valid schedule for n-1 years. So that means there are n-1 cases of this type. Now let's go to the other case. If the last year is 1, 3, 2. Now here, for the n-1 year, we need to consider the requirements, the rule. Because before 3, it cannot be 2. That means the 2 on the n-1 column must be on the top. 2 must be here. And the 3 is here. So that means the nth year determines n-1 year. n-1 year is not totally free, not like the previous case. So after that, we know that the early years are now free. This part can be any valid schedule for n-2 years, right? Because 1 is before 3. We will not have 1 after 1, and we will not have 2 before 3. So all requirement will be satisfied. As long as this part is a valid schedule for n-2 years, that means there are a n-2 cases. Now, those two cases covers all possibilities for n-year schedule. And the total number we know is an. So an equals an-1 plus an-2. That's the recurrence relation here. Now let's apply recurrence relation to solve A8. Here we have A1 equals 2, A2 equals 3. From that, let's solve all other ANs. So A3 equals A2 plus A1 is 5. A4 equals A3 plus A2 equals 8. And A5 equals A4 plus A3 equals 13. A6 equals A5 plus A4 it is 21. A7 equals A6 plus A5 is 34. Finally, A8 equals 34 plus 21. So A7 plus A6, 34 plus 21, 55. So we have A8 to be 55. That is, if you fix the schedule for ones, there are 55 ways to schedule 2 and 3. And then if we come back to this answer is 6 times A8. So it should be 6 times 55. It is 330. So in this way, the answer to the question is 330, which is D here.